Okay, today we are looking at section 1.5. We're going to look at examples 3 through 7, and this is going to be about inverse relations and functions. So before we actually get into the examples, we're going to talk about what an inverse is. An inverse means it undoes. So at some point in your life, you've learned sine, cosine, and tangent. Well, so cosine, just to review, cosine equals adjacent over hypotenuse. The inverse of cosine is taken of the adjacent over hypotenuse to give me the angle. An inverse function undoes. The inverse of multiplication is division. So when you solve an equation, you have 2x equals 17. You divide by 2. Inverse of addition is subtraction. The inverse of squaring is the square root. So inverse functions undo each other. Sometimes we're going to say inverse relations because not all functions have an inverse that is a function. Okay. So the other thing we can talk about for inverses is they switch y and x. So if I give you a table, I'm going to call it a relation. Remember, a relation is just any relationship. A function is one where each x has its own y. Okay, so no x goes to 2 y's. So this is a function. Its inverse literally means switch x and y. I'm going to come back to that graph after I do this. And this one's inverse also happens to be a function. Okay. If I'm talking about graphically, the inverse to switch x and y, I reflect over y equals x. This reflected over y equals x is that. Now, notice the red one is going to fail the vertical line test. The red one is a relation. It is the inverse of y equals x squared. However, it is not a function. So hold on. To find the inverse, I switch x and y. So x equals y squared. Actually, let's write that in red. X equals y squared. When I solve, I get y equals, I must include this plus or minus because the square root to make it a function only keeps the positive case of this. So the square root as a function is just this positive part. It'd be the same graph, but I'm tracing it differently. The negative is the downward one. So on the original, I can apply the horizontal line test to check if its inverse will be a function. The horizontal line test is functionally the vertical line test on the inverse. So if any graph that I need to check if it's a function, if its inverse is a function, I check with the horizontal line test. We're going to find some inverses algebraically. The notation This only applies though if it's a function. Is f inverse of x, that means find the inverse function. So f of x here is x over x plus 1. To find the inverse, first thing I'm going to do is I'll write f of x as y. You may not need to do this step, but somebody might. So then, if you do, please take the time to write it. Switch y and x. So all the y's become x's, all the x's become y's. Now I get the fun part of solving this for y, because f inverse of x is essentially in y equals form. So to solve for y, I'm going to multiply both sides by y plus 1. And that means I'm going to distribute it to both sides, giving me x, y plus 1 equals y times y plus 1 over y plus 1 just cancels the y plus 1s. I'm going to go ahead and distribute. I'm going to subtract x, y from both sides to get the y's together. Yes, I'm separating the x's. I'll bring them back together later. The reason I need to get the y's together is here I'm going to factor out a y, because y is common to both of those. Now I can bring the x back together and isolate the y by dividing by 1 minus x on both sides. Y is equal to x over 1 minus x. My inverse, that should still be a function. F inverse of x is x over 1 minus x. So the key here, and anytime I'm giving you a test, if you correctly switch x and y, make it to this step, that's worth half credit. Okay? And that should be the easy step. Sometimes solving them is kind of hard. Here I had to move my denominator and gather the y's together to factor. So solving this was not easy, but the switching y and x part should be pretty easy. And this technically is the inverse, it's just not in a nice form. I can't plug that into my calculator because I need it to be in y equals form. Okay, now we're going to talk about a 1-to-1 function. Okay, 1-to-1 means, so normally for each x, there is one y. 1-to-1 also means for each y, there is one x. So, probably done some like this before. And this is a function. Each x goes to one y, but it is not 1-to-1. Each x does not go to its own unique y that with no overlap. So the y's don't all correspond. I don't think I said that right. The y's don't all come from only one x. 1-to-1 is going to apply that each of these goes to its own y. What does that look like on a graph? Well, a 1-to-1 function has to pass both the vertical line test to be a function and the horizontal line test. So that means a 1-to-1 function is a function. And its inverse must be a function. Okay, so that is the thing with one-to-one. So again, finding the inverse is simply the reflection over y equals x. This is roughly example 5. So my function is in blue. Call it f of x. Well, we'll call it g of x. I made a g. Its inverse going to be here in red. G, since it's a function, I can label it with inverse function notation. Okay. Proving two things are inverses. I can't just calculate the inverse of one and see if it's the other. That's not a proof. So to prove things are inverses, we're going to have to use our function composition. F of g of x, which means f of g of x. Oops. Of g of x must be equal to x, and I must prove it the other way. G of f of x, which means this, f gets plugged into g, must also equal x. So here are my two functions. F of x is going to equal x cubed plus 1. And I'm going to prove this, that these are, it's example 6. And g of x equals cube root of x minus 1. So let's start with f of g of x. Let's put it over here. So again, that's f of g of x. I'm going to skip writing that step. But g of x is f of cube root of x minus 1, which is g of x. Okay. So means I'm plugging the cube root of x minus 1 into my x and f. Well, the cube root and the cube just cancel out. That's x minus 1 plus 1, which definitely equals x. Check mark. This one's taken care of. Now we got to do g of f of x. I have to do both ways. This usually, if one way works, the other way works, but not 100% of the time. So I have to check them both. G of f of x going in is x cubed plus 1. Finish that in blue. Make my colors match. So I've got the cube root of x Let's make that red again. In for x goes my red x cubed plus 1. X cubed plus 1 minus 1 is the cube root of x cubed, which does equal x. Both of these check off. These are inverses. We'll do another example of finding an inverse function. So, and a little bit of domain restriction, so the inverse is actually correct. So here, f of x equals the square root of x plus 3. And that graph, you can check on your calculator if you need, but is a square root that's moved to the left 3. Now, the domain of this is -3 to infinity. The range, oops, that's not a range, that's not an R. The range is 0 to infinity. So to find the inverse, I switch y and x. And again, I'll write it with y equals instead of f of x. If I'm doing this myself, I probably wouldn't. But I want to put in that detail here. So if you don't need to do that, that's fine. Okay, to solve, so now I've done point 1. I've correctly written an inverse where I switched x and y. Now I solve. To get rid of the square root, I'm going to square both sides. As long as I do it to both sides, I'm fine. Giving me x squared equals y plus 3. And to get it into y equals form, I'm going to subtract 3 from both sides and get x squared minus 3 equals y. So that graph, x squared minus 3 equals y is going to look like a parabola. But that wouldn't look like a reflection over y equals x if I had the whole thing. One of the important characteristics of inverses is we switch domain and range. So this domain from my blue one, my original function, becomes my new domain. My range, my domain from the original becomes my new range. So swap those two. And my result is I only get half the parabola. F inverse of x is not x squared minus 3 unless I restrict the domain, because I don't know why I did that. Because my original didn't have all of that in its range. Okay. Sometimes inverses do not have the full domain of what's normally written there. Okay. This was example 7. And that is section 1.5.